Hello, everyone, and a warm welcome to our Fellows Public Talks. I'm Claudia Rizzini, the Executive Director of the Radcliffe Fellowship Program at Harvard University. It is my pleasure to introduce Laura DeMarco, Radcliffe Alumnae Professor and Professor of Mathematics at Harvard University. For many of us, math is a rusty reminder of our high school days, or the skill set we vaguely remember when we're asked to calculate a tip at the restaurant. But for some, the landscape of pure mathematics is a vast universe with exciting frontiers. Laura DeMarco is one of these intrepid math researchers, exploring the beautiful and unexpected connections at the intersection of number theory and dynamic systems. Dynamical system research can be seen as the mathematics of change, the study of things that evolve over time, from wildlife population within a state park to the movement of the planets in our solar system. But while concepts of dynamical systems are best explained through applied real-world examples, Laura's work also embodies the pure principles of number theory, which studies the fundamental properties of numbers. How do very simple formulas yield incredibly chaotic behavior? And how do the deep, intrinsic qualities of numbers influence and shape the structure of complex, evolving systems? These questions and more capture the curious spirit of Laura's research and her project at Radcliffe this year. She hopes this glimpse into her world will illuminate the human creativity that is essential to pure mathematics and will encourage others to experience the wide universe of mathematical discovery. The Q&A portion of the public talk today will be moderated by Martin Wattenberg, Gordon McKay Professor of Computer Science at the Harvard University School of Engineering and Applied Sciences. And now please join me in welcoming Laura DeMarco.
Thank you, Claudia, for that introduction. Thanks to all of you for being here in person and on Zoom. Of course, I'm delighted to be spending the year at Radcliffe, and I'm grateful for the support, of course, both for my research and for the whole community here. In order to describe my Radcliffe project, I want to begin by showing you a few images, such as the one you see faded in the background here of my title slide, that have come up in my recent research projects. So I spend a lot of time creating and studying pictures like these. Each one of these is a visualization of some piece of mathematics, and sometimes that math doesn't have an obvious shape or geometry, and so I try to find it. Because of course I'm hoping that the picture will help me understand the math better. And obviously the better we understand the math, the more we can do with it, the more powerful it becomes to answer questions and solve problems. So I don't intend to create art, per se, but somehow and sometimes the pictures are surprisingly beautiful, at least to me. And so I decided to center this presentation today around one of these images. So this is one that I generated about 10 years ago for a project, but turns out to be closely related to what I'm doing this year here at Radcliffe for my project. And I'll tell you what this is in roughly 20 minutes from now, or maybe 30 minutes from now. But I want to draw your attention to a few features. Now, I should say it really surprised me when I created it because it looks like an eye. I wasn't expecting an eye shape, so that already was something. But the features that I'm interested in, or that I really was focused on, was the symmetry in the picture. So you might notice that it's perfectly symmetric top to bottom. If I flip the picture, it's the same picture. And it's almost symmetric, right, left. If I flip the picture the other way, it's not quite the same picture, but it's similar. Because you'll see, there are some decorations here on the outside of the eye on the left side, and then you see some kind of stuff on the inside of the eye on the right side that doesn't appear on the other side. So it's not perfectly symmetric left-right, but it's very close, and this was meaningful to me in what I was looking at. And also, I want you to see the structure of one of these decorations. So as I zoom in here, you'll see that that decoration takes on a very particular shape. In fact, a very famous fractal shape, so famous that it has a name. This shape is what we call the Mandelbrot set, a super famous object in mathematics. It's been studied actively for nearly 50 years now. So I'll come back to this picture in a moment. Okay, so my project. I'm studying sequences of numbers that are generated recursively. And one of the most basic examples of these, and one of the most famous examples of these, is the Fibonacci sequence, which some of you might have seen before, might have played with as a student at some stage. So what is the Fibonacci sequence? So we start, say, with these two numbers, 0 and 1, and the rule to generate the sequence, step 1 is to add the two numbers together, and in this case, we get 1. Okay? And then at every step of this process, we add the last two numbers together to produce the next. And we repeat in this way. So at every step, you take the last two numbers that you've created, you add them together to get the next one. 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, etc. Okay? So hopefully, there is a rule. It's an example of what we call a linear recursion to generate this particular sequence of numbers. And you can set up your computer easily to generate as many of these as you would like to see. Now, if you don't know anything about the Fibonacci numbers, and say you go online and you do a search for them to try to get information, you will very likely see images like these. Okay? So this suggests that somehow the Fibonacci numbers can be used to encode some aspects of the natural world. In this case, it's these spirals and the structure of these fractal-like pictures in nature. And indeed, the Fibonacci numbers can be used to encode this, but that's not what I want to talk about today. Okay, so I want you to look at the numbers themselves. Okay, so I want to focus on the numbers themselves. Okay, so what do I mean by that? Let's focus on just this first row of numbers. You might notice that 4 of these numbers are prime. Okay, prime numbers. Now remember what a prime number is. Probably haven't thought about prime numbers in a long time. So a prime number is a number which is at least 2, but which cannot be written as a product of smaller numbers. Okay, so it's prime, and this is a fundamental building block for multiplication. Okay, so 8 is not prime because you could write it as 2 times 4. They're both smaller than 8. In fact, you can break it down even further into its prime factors. It's 2 times 2 times 2. All right? 21 is not prime because you can write it as 3 times 7. Okay? Those are its prime pieces, its prime factors. But 13 is prime. You can write it as 13 times 1, or you could write it as 1 times 13, but you can't write it when both of the factors are smaller. Okay? And there are a few more primes on this slide. Which is interesting, and if you keep going in the Fibonacci sequence, maybe you'll find more. But it turns out that if you look more deeply into these numbers, and in fact into these prime factorizations, like I've written here, you'll start to see really interesting patterns arise, some very surprising patterns that illustrate some type of complexity, which is generated by this particular sequence. Okay, a sequence that was very simple, remember. All I did was add the last two numbers to produce the next. So to illustrate this complexity, okay, so on this slide, I've written out the prime factorizations of the first few rows of my Fibonacci sequence. Okay, so some of the numbers are prime, so there's no factorization there. But for all the ones that are not prime, I've written out their prime factors. Okay, so I would like you to look at this sequence of numbers that you see on this slide, and I'm going to, one by one, highlight them in gold if it's the first time that a particular prime number appears. Okay? So for example, so primes have to be at least 2. Okay, so I'm going to forget about the zeros and ones. But as soon as I hit 2, it's prime, 3 is prime, 5 is prime, and they're all different. They're distinct numbers. So I put them all in gold. But then when I hit 8, its only prime factor is 2, but I've already seen 2, so no gold. Okay, so, and then I keep going. So again, at every step, I'm going to highlight in gold a prime factor if it's new, if I haven't seen it yet. Okay, so I'm collecting all the new primes that appear in the sequence. Okay, so 17 is a new factor, 11 is a new factor, 89 is itself prime, haven't seen it yet. Look, 144, its only prime factors are 2 and 3. I've seen them already. I skip it, I move on. Okay, so do you see what I'm doing? At each stage, I'm going to highlight prime factors in gold if it's new. Okay, 2584. 4181 happens to have 2 factors, which are new. Fine. And then we keep going. Okay, so if you continue in this way, you just keep on going in your Fibonacci sequence, you will see that you're going to see a lot of gold. At every step, you're going to see at least one new number, suggesting that there's something rich and complex about this sequence, that it's exhibiting some very interesting complexity with all these new numbers. Any old sequence is not going to have this feature, but this one is generating a new prime factor, it's seemingly at every single stage, some kind of feature of arithmetic complexity. And indeed, it really does, in the sense that it was proved more than 100 years ago by a mathematician named Carmichael that yes, at every single step of the Fibonacci sequence, except those 2 exceptions, 8 and 144, you will see a gold number at every single stage, no exception beyond 144. So he was able to prove that for this very simple linear recursion, we're generating a lot of interesting richness, this arithmetic complexity for this sequence. By the way, just a remark, because I think it's fun to notice, actually you get every single prime number this way. Like, let's say your favorite prime number is 239, and maybe yours is 37, and you will find that number somewhere in this sequence. Like, I don't know where 239 appears, but it's going to be somewhere in this sequence. So every prime number, it turns out, will come up as a factor at some stage, and that's not very hard to prove. But Carmichael's observation about the complexity is a more involved statement, and it's actually very interesting. I should say, I have no idea if Carmichael himself was actually interested in the Fibonacci numbers. He was studying these linear recursions more generally. There's a large class of such recursions, and this is just one example where this happens. I want to show you one more example, just so you can get a flavor of what types of sequences might have this feature. So here's another example, which is covered by Carmichael's work on linear recursions. So let's say I start with 0, as I did before. And now the rule for generating the sequence is to double the number and add 1. Okay? So it's quite simple. At every stage, I double the number and I add 1. Double the number and add 1. Okay? So I get 15, and then I double it, I get 30, I add 1, I get 31, I double it, I add 1, etc. And just as before, I can use this to generate some infinite sequence of numbers, and you can go out as far as you want. And it turns out that Carmichael's theorem, the result, also holds for this sequence. Okay, so this is just one of the many examples of types of recursions, of sequences, of linear recursions that Carmichael was studying. At every step, with one exception now, this is the number 9 times 7, or 63. So there is exactly one exception where I don't get a golden factor, a new prime. But at every other step, you'll actually have a new prime factor. So it's interesting that he was able to prove a statement, as often the case in mathematics. You want a statement, you want to prove a result, you want to know a result is true always, like at every single step. But it's subtle because there can be exceptions. So then, of course, one has to study what are the exceptions and why are they there and what's causing them. So that's also involved in sort of this package of work that he was doing at the time. Okay. So this is 1913 that he proved this, or published it in any case. So nowadays, we're interested in looking at all sorts of recursions like this, not just linear recursions, but much more complicated recursions, maybe some nonlinear recursions. The world is not linear exactly, and so it's very natural to ask similar questions about this type of complexity that can be generated by these sequences in other settings. Okay, so I want to give you just a few examples. Okay, so bear with me, a few more slides of numbers that I want you to look at. So here's just an example of a very simple nonlinear recursion. I want you to take a look at the numbers here. So here the rule, again, I'm starting with 0, just for simplicity. The rule is you take the number, you square it, and you add 1. Okay, so remember, last time I was doubling the number and adding 1, and that was a linear recursion. Now I'm squaring the number, meaning you take it and you multiply it by itself and add 1. So at every stage, I square the number, I multiply it by itself, and add 1. 26 squared, you can do that in your head. All right, and you keep going. Whoa. Okay, and one thing you'll notice is that these numbers get very big because I'm squaring, right? So if you take a big number and you square it, the number of digits will double, roughly double. So these numbers are getting very big very fast. So, okay, they don't fit on my slide, fine, it doesn't matter, but we can still study their properties, even if maybe I can't write them down. So, or at least not with this font on this particular slide. So, okay, so let's say we decide to look at the same properties. What are the prime factors here in this particular sequence of numbers? Well, here they are. I've written out the first prime to appear is the number 2, and then 5, 13, 6, 77 is actually prime. And then you keep going. Whoa, and look at that. There's a lot of gold on this slide. And remember what gold was. It was I colored it gold if it was the first time I'm seeing a particular prime number appear in this sequence. So this example of this nonlinear recursion, because it's involving squaring, so that exponent of 2 is what makes it nonlinear. Exhibits already quite a lot of interesting arithmetic complexity with all these new prime numbers appearing, and a lot of them at each step. One thing that's actually quite different in this example than the linear ones I showed you is that not all the primes will arise. In fact, very few of the primes arise. So there's a way that we can quantify how many arise. So there's an infinite list of prime numbers. So that's easy to prove. So there are lots and lots of prime numbers. And here, we're only seeing a very small proportion of them. There's a notion of density of the primes, and this has 0 density as opposed to 100% density. Very few. There are a lot of gaps in the sequence of primes that actually arise, one can show, which is a very interesting property in and of itself. But again, not the focus of today's presentation. But nevertheless, we're seeing a lot of gold in this sequence. And by the way, there are no exceptions. Once you hit that first prime 2, there are no gaps. There's a prime at every sequence. It turns out one can prove that. It's not too hard to show for this particular example. Let me show you another few examples so you get familiar with these nonlinear examples. Let's start with 0 again and square the number, and instead of adding 1, I want to subtract 1. Okay? So we can work with negative numbers just as easily as we can work with positive numbers. When we repeat, though, and we square -1, remember we get back to 1. And so look what's happening here. This one is a really boring example. I'm just going to, yeah, there it is. Okay, there are no primes or prime factors at all appearing in this particular sequence. But okay, it's just because I made a bad choice. It's actually very easy to cook up bad examples that just go nowhere. There's obviously no arithmetic complexity in this sequence 0, -1. I mean, it's just boring. There's nothing happening. So it just repeats. So maybe I want to avoid those. So one would have to understand which ones are going to lead to these bad examples or boring examples, and when can we guarantee that we're going to have something interesting happen. One last example with numbers that I want to show you. We can also, of course, we can work with negative numbers. We can also work with fractions, with rational numbers. We don't need to restrict ourselves to whole numbers. So just as one more example, in the same family of examples, squaring plus a constant. Square and add some number. So here is where I'm just squaring and adding 1/2. Okay, so we can do it also with fractions. If you remember how to add fractions, that's all you need to remember. And here we go. We can start to do it. 1/2 squared is 1/4, plus 1/2 is 3/4. 3/4 squared is 9/16, plus 1/2 is 17/16, etc. So we can keep going, and you just get a sequence of numbers just as before. Although now you have numbers in the numerator and the denominator, so you could look at the primes in the top and the bottom, if you wish. And just a remark, in this case, again, it happens that at every single step, it turns out there's going to be a new prime factor. So it turns out the conclusion of Carmichael's theorem from more than 100 years ago holds for this example too. His proof does not hold. The theory that he developed and was using to show a result for linear recursions definitely does not have any bearing on these nonlinear recursions, but it's interesting to observe that the conclusion ended up being very similar, the type of observation you can make about this sequence. Okay. So, what's going on? How should I, as mathematician, exploring all these examples? I have a bunch of data. There's so a lot of patterns that I'm starting to see. How could I possibly explain these observations? And so in this case, what that meant very precisely was, when does a given recursion generate complexity? When might it generate lots and lots of prime factors? Which primes can arise? How can I distinguish between the good ones, meaning where complexity is generated, and the bad ones, where maybe it just cycles or terminates or nothing interesting happens? Is it possible to prove, mathematically, convincingly prove, a version of Carmichael's theorem for these types of nonlinear recursions? So these are the types of questions one might ask in this case. But maybe a very important question one should ask is, and why do we care? Is this interesting? Is this useful? Does it connect to any other type of mathematics? What's really going on? And this is a question, of course, I care a lot about. What makes mathematics or certain types of mathematics interesting and which ones are not? This is a big question. And I'm hoping that as I go on over the next few minutes to explain what's really going on behind the scenes here, it is actually interesting, and it's actually connected to a lot of other mathematics. That I'm presenting a statement about sequences and prime numbers, but there's a lot hidden underneath. And part of that can be seen, that hidden stuff can be seen with those pictures that I was showing you at the beginning. Okay, so the pictures. So this, the famous Mandelbrot set, is one way that we as mathematicians might picture or visualize those sequences, those particular nonlinear sequences that I was showing you. Okay, this is supposed to somehow capture information about the sequences that I showed you. Okay, so what is this? What is this? So this is a two-dimensional picture now. I was talking about sequences of numbers. Now I'm in some two-dimensional space. So you can imagine you have an x-axis and a y-axis. But I want you to think of this not as pairs of numbers, but as one space of complex numbers. Okay? Every point in this space represents a single number, which has what we call a real part, given by its x-coordinate, and an imaginary part, given by its y-coordinate. Okay. So here, I'm asking you to take some type of conceptual leap with me. I I had started talking about just numbers, regular old whole numbers, or maybe fractions, rational numbers, numbers in the usual sense. And now I'm saying, come with me into this bigger world, expand your vision to think instead in the world of complex numbers. And by expanding this field of vision, working with this world of complex numbers, maybe we can actually get more information and we might have more tools to use to analyze those sequences. And it turns out we do. By the way, you can do arithmetic or algebra with these complex numbers just in the same way that we do in real numbers. You can add them, subtract them, multiply them, divide them. You can do all the same things with these complex numbers. You just need to remember that I squared, I times I, is -1. That's the only rule you need to remember, and then you can do all the same algebra that you would with the familiar numbers. Okay, so I'm thinking of this picture as living in the space of complex numbers, and then I can build my recursions also with complex numbers. All right? So now I want you to picture that every point in this space is generating some sequence of numbers, and generating them by this rule. This is the same rule for those, this is just one example, but this is the same rule for those nonlinear recursions that I was showing you earlier. You start with 0, you square the number, and you add a particular constant. But in this case, my constant is complex. Okay? So I'm just doing the same rule, but with complex numbers. So I want you to picture that at every point in this two-dimensional plane, you have a sequence of numbers somehow coming out at you. Okay, so third dimension. At every point in this plane, there's some sequence that's generated, associated to it. Okay? Now, the Mandelbrot set, what's depicted here, this fractal image in black, has a very simple definition. I've written it with set notation, which I realize is probably not familiar to everybody in this room, but what does that mean? It's by definition, the Mandelbrot set, the points in black, are exactly the complex numbers for which, when you generate that sequence, it's bounded. These numbers themselves never get bigger than 2. They stay small, in some sense. Their magnitude is controlled by 2. There's a sense of size of a number for complex numbers, just as there is for real. It's the same as the absolute value that we think of, that we learn about real numbers. Okay, so it's just the set of sequences, the set of parameters C here, for which the sequence you generate never gets bigger than 2 in its absolute value. Okay. All right, so this is actually a very simple definition, and in approximately, let's say it was 1979, when the first computer image of this Mandelbrot set was created, and it was a big surprise. Maybe in 1979 it wasn't such a great image, but certainly by 1980, on the record and in publications, there are versions that look very similar to this one. So computer graphics had developed sort of just enough that people could draw a picture like this. It's a very simple algorithm to do so. And the big surprise is that from such a simple rule and a kind of naive, simple definition, you get this wild picture, okay? This fractal, wonderful image. By the way, the color, so the Mandelbrot set is actually just the part that's in black, and all the coloring outside is there to help you visualize where the black is. You can't quite tell, but there continues, I mean, here I've covered it up, but there continues to be black moving out here, out to this point, which is at -2. And there's some stuff happening in between. And the colors are just supposed to help you see the complexities and the interesting shape that's there in the Mandelbrot set. So we use a particular algorithm to draw this picture so that you can see some of that structure. If it were just a black and white image, it would be harder to visualize. Okay, so the sequences that I was showing you earlier, that I was generating with actual numbers, familiar numbers, they all come from the x-axis. So this x-axis records, these are the real numbers in our complex space. Okay, so these are the real numbers. So the point is that for any point, remember, for any point, I have an associated sequence that I'm thinking of as a string of numbers that's coming into the third dimension. And here's just some formula for it. Okay, it doesn't matter. It was just the rule itself. So for example, here I'm at what? I'm at roughly -1 3/4, -7/4, and that generates this particular sequence. Okay? So every point in the axis for the real numbers, here I'm at 1/2, and that'll generate this sequence. If I move, say, over here to -1, that was one of my bad sequences, remember. If I did this same rule, starting at 0 and then -1, then I just get that periodic sequence that has no complexity, it's boring, it's what I call bad. And in fact, a lot of the sequences that you generate turn out to be bad in the sense that they will eventually repeat or maybe even come right back to 0, like these examples. So 0, -1, -2 happen to be examples that give you a bad sequence, a boring sequence. And you can set your computer up to plot all of the bad C values. So here, I set the computer to draw for me, to put a little yellow dot on every single complex C that produces a sequence that eventually repeats. And that's what these little yellow dots are. And you can see, I don't know if you can see them, but there are lots of them scattered around. In each of these black regions that you see, you're going to find a yellow dot. There are lots and lots of ones that actually repeat, that I'm thinking of as bad because they're not generating this arithmetic complexity. They're not generating complexity at all. They're not generating anything. They're just stopping after a finite step. Okay. And you can't quite tell, but so this Mandelbrot set, one of the wonderful things about it is it's a fractal in the sense that it exhibits certain self-similarity features. It's not actually self-similar. When you zoom in different places in the fractal boundary, you will see different things, but you will always see little copies of the Mandelbrot set at all scales. It's just that the little copies come with some extra decorations. And so this is one of those little copies, and you can see that every one of these little copies will also have a bunch of little yellow dots. So in other words, I wrote here, there are lots of these bad, I said X's, but really I should have said C's in the complex. But it's also the case on the real axis. There are infinitely many yellow dots scattered along the real axis as well. Okay, so there are lots and lots of these yellow dots. Okay, how much time do I have? Okay, there's one quick thing that I couldn't resist, and I wanted to include this slide. This is, in some sense, really for mathematicians who may be watching, but just to share that these yellow dots are actually at the heart or the center of a very important question in the field of dynamical systems that I don't have time to get into during this short presentation. But there's a major open problem in my area, which can be formulated in terms of the location or geometry of these dots scattered around the space. There's a conjecture. A conjecture in mathematics means here's a statement that we believe is true. All evidence points to its truthness, its truth, but we don't know how to prove it rigorously mathematically. And this is one of those types of statements. It's very important because of the role that this Mandelbrot set plays in understanding dynamical systems more broadly. And so I just wanted to mention there is an important conjecture, and it can be formulated, forgetting about what the conjecture actually says and understanding the definitions, not relevant for today, but that question can be reformulated in terms of the location of these yellow dots. If I knew that every little black blob in the Mandelbrot set actually contains a yellow dot, that would be one way to actually prove what's called the density of hyperbolicity conjecture. Anyways, I want to, wow, time goes so much faster when you're, how is that possible when you're on the stage? Okay. Geez, I'm going to run out of time. Okay, I want to bring you into 21st century mathematics. I wanted to share with you a result, one theorem, just to state one relatively recent theorem. And this is a theorem which is due to Holly Krieger, who was actually one of my first PhD students, and she completed her degree in 2013, and she was able to prove, okay, what does this statement actually say? I'm not going to read it, but it says, the analog of Carmichael's theorem for this collection of nonlinear recursions. And it's what makes it actually very subtle and very interesting is that, like with the Fibonacci numbers, there can be some exceptions. There can be up to 2 steps along the sequence where there's no golden prime, where there might not be a new prime. But at every other step along the sequence in this particular family of recursions, you can generate a new prime. So there's lots of interesting complexity. The only sort of bad choices when you deal with rational numbers are 0, -1, and -2, and every other one is good. And I wanted to mention this as an illustration of, as I said, 21st century mathematics. This is not a result that Carmichael could have proved, or any of his colleagues in that day, or even in the 1980s when we started studying the Mandelbrot set and got a lot more information. No, this is really, the proof and the techniques, it really involve some very recently developed theory in number theory for understanding features of these primes, and in complex analysis for understanding features of the Mandelbrot set, and some combination of tools. So I just want to mention. And there's one thing else I want to mention before I move on. A little shout out to the Radcliffe Institute, because Holly Krieger was here as a Radcliffe Fellow in the 21-22 academic year. And while she had proved a version of this theorem in her PhD thesis, which was completed in 2013, she improved it that year while she was here. So this is one of the many things that she was able to accomplish and to prove while she was here as a Radcliffe Fellow. So another, thank you to the Radcliffe Institute for supporting that work, because it was actually really impressive that she was able to get the full statement, which was the analog of Carmichael's theorem, but using all sorts of modern tools now, very different techniques than what Carmichael was using. Okay, I have 5 minutes left, and I'm supposed to now tell you all about my project for this year. No, I'll just say a couple words. All right, this I, what is this I? This I is the analog of the Mandelbrot set, but for some other recursion. The formula doesn't matter, but it's some other recursion, and it's some family of them where this C value here is some complex parameter shown in this picture. Okay. Now, what I'm actually working on is a way to distinguish or to determine the dependence or independence of, say, 2 different sequences with different initial conditions. Okay, so for example, I could build a recursion starting at 0, like I had done on the previous slides, or I could start with 1, or maybe I could start with -1. I can start with different initial seeds and run these recursions, and I'm trying to understand how does one detect a notion of independence between the sequences that we generate. And it should be that if the starting points are sufficiently unrelated, they're different from one another, that the badness should be unrelated, that at least one of the sequences should be good. So maybe the point, starting at 1, I can generate this arithmetic complexity by running my recursion. Or in another case, in another example, I'd run with 1 and I hit some badness and I'm getting some cycling and it's not doing anything complicated, but -1 will then win. So one or the other should always be good. So if they're unrelated, at least one of them should be good. So if you just sort of run your recursion with 2 starting points, that might be enough to guarantee some kind of arithmetic complexity. And this example I chose and wanted to understand because it was one of the worst case scenarios. Because this picture, represents some feature of this recursion, and this was a picture associated to starting point 1 for this formula. But the flipped picture was the picture associated to -1. And the 2 pictures are very similar. They're not exactly the same, as I pointed out earlier, but they're very similar. So I was thinking of this, indeed, as a worst case scenario, where the 2 points, they don't give quite the same thing, so they shouldn't be related to one another, but they're so similar that maybe there's trouble. Maybe there's trouble nevertheless. But can I guarantee that if I run the 2 recursions simultaneously, that at least one of them will be good? And that's the type of problem that I've been thinking about very recently. It turns out in this case, yes, one can prove that there are only a handful of recursions in this family for which both of them are bad. It is rare for both to be bad because the picture is not symmetric. They're not the same picture. Okay, so the idea is I'm going through, this was this conceptual leap, I'm making a transition from a statement about numbers and algebra and sequences and badness to the geometry, the shape of the space and the asymmetry of the space, and somehow to use that asymmetry to say that the badness is unrelated. And one more thing I wanted to say about that example is that distinction, the asymmetry, is actually witnessed by this shape. Now this shape, remember, this was a different recursion. Remember, I gave you a formula. This Mandelbrot set shape comes from those quadratic polynomials, and the I is coming from a totally different collection of recursions. But nevertheless, it is the Mandelbrot set which is acting as this certificate or stamp of approval of independence. That Mandelbrot set is there, but it's not on the other side. It only appeared on the left side, and it is the shape, it turns out, which is detecting for us a distinction between the 2 points. And so I'm playing around with these ideas of how to exploit this geometry and these familiar fractal shapes, which are really representing bifurcations in some family of dynamical systems, in order to make conclusions about the algebra. So there was one last example I had wanted to share, but I want to share it. I will say a few words because I said the other was essentially a worst case scenario, but actually this one was really even worse because this picture really appears to be symmetric. It looks completely symmetric right to left. And one of the pictures, the original one, say, is the one you get from starting at 1, and the other is associated to the sequences starting at -1. I've only changed the formula very slightly. The formula doesn't matter. Don't even bother reading it. It's just some recursion, okay, some family of nonlinear recursions. But this one has a lot of symmetry, so then I thought, oh, does that mean that the sequences are actually related to one another because the picture appears to be the same? But it turns out, 10 seconds, it turns out that the visualization is just the wrong visualization. And if we look at something else, if we basically, it's like taking an X-ray of a person. I have like the original picture was like taking a photograph, but if you redesign your algorithm and rethink about the mathematics, you can look at it differently and you can get a lot more information. So this is just a sort of a cautionary tale that sometimes looking differently at something gives you more information. I'm forced to stop now because I've hit the 40-minute mark. So I can't show you that there really was a little Mandelbrot set in there that detected that independence and that asymmetry. It's on one side, but not on the other. These are reflected images. It's only on one side and not on the other. So I'm forced to stop. I had all sorts of things to say about real life and how this is supposed to be connected to things that you might be interested in, but I hit my 40-minute mark, so I'll stop here.
All right. Thank you so much for this fantastic talk. I learned a lot. And I'm going to get to some audience questions in a moment. But I want to start out with one question that, I was really taken by the visualizations. This is a field that is very dear to me. I want to hear more about how they figure in your process. Like, do you look at something and see asymmetry and say, aha, that's a proof, I'm done? Or to what degree is it an iterative process with making these, X-rays or alternative views?
So the short answer is definitely not done with the visualization. Like, visualization is step 1. Or maybe it's step 2, because first you have to understand what to visualize. You have to look into the problem and then figure out what to picture. But the picture is just for guidance. It's just for inspiration. And then, indeed, maybe it is an iterative process that I need to picture something else. But even that's not going to be enough. So there's the step that's beyond making the picture. So the picture gives me ideas. It might even suggest what the mathematical route is to an actual proof, but it's essentially never a proof because what you're only ever seeing a piece of what's going on by drawing this picture. It's a finite amount of information that you can even create or visualize on the picture, in the picture. But for the mathematical argument, I need some logical argument to build on what's known and what sort of step-by-step logical reasoning convincing argument. I have to be able to convince others that it's true not just for the parts that you see in the picture, but it's always true.
Right, partly because the pictures can be a little deceptive, it sounds like.
And they can be deceptive. So I could have concluded in that other example, they're symmetric, therefore they're going to give the same types of sequences, and then it turned out, no, actually, they're not the same, and there's something else going on.
Fascinating. I'm going to turn to an audience question, and there's a question about relations between the Mandelbrot set and some of the other sets you talked about, and cryptography, and like sort of generating keys for codes. And the question basically is asking about inherent structures of these number sets that make them good for cryptography. And in fact, could we hope that maybe this could help us, withstand quantum attacks? This is above my pay grade, but I'm curious.
So I'm not an expert in cryptography by any means. Let me say that no, these particular sequences that we're generating will probably not be so good for creating some kind of crypto system. But there are some interesting connections between the type of math that I'm doing here and how people do design some powerful crypto systems. Like even the most basic sort of public key cryptography, like what's known as RSA. It's one that we teach to our students, which is involving the process of factoring big numbers into a product of primes. And that's a much harder process. Its complexity is much greater in the factorization process than in the multiplication process. So it's easy to multiply two numbers. There's a simple algorithm, but it's harder to factor two numbers. It's a harder process. So that's a mathematical thing that's useful in cryptography and is being used in current, for exchanges on the internet and, making your transmitting your credit card information. But that's not going to defeat a quantum computer. And so once quantum is in place, assuming that it will be, and it probably will, other systems are needed. And so there are things like lattice-based cryptography and other ideas that are out there that are expected to be powerful enough. And they're also math. And they're also building on prime numbers. And maybe they're working over some ring that's generated with coefficients in some finite field, which is somehow, there's prime numbers underneath that. So anyway, so there's some stuff there that's related mathematically, but it's not, I don't think that this particular generation of complexity is directly going to be useful for a crypto system. But again, I'm not an expert, so I don't know.
That makes sense to me. In fact, I might sort of riff on this question and say that it raises this issue of what are applications? How does this relate to the rest of life? And you mentioned that at the end of your talk, so maybe I'll give you a chance to sort of talk a little bit about that.
I did want to say a few words about dynamical systems in real life, whatever that should mean. So there are a lot of examples where recursions, whether linear recursions or these nonlinear recursions, actually come up in these are sort of models of real life systems. And one of my favorite examples is the solar system and the motion of the planets around the sun. And so abstractly, one can think of sort of simple, relatively simple models for the motion of the planets around the sun, described as one model for this is what we call the n-body problem, where you have the motion of n objects in a space, and they're subject to the force of gravity. Forget about relativity. Let's just try to keep it simple and just talk about gravity. But already, it's an extremely complicated dynamical system as soon as you have at least 3 objects. Maybe some of you have seen the series, The 3-Body Problem, or read that book. I mean, it was all on the premise of this chaos inside of a rather simple dynamical system, which is what these models in the Mandelbrot set and the things I was talking about are trying to get at, is to understand, for very, very simple models, what kind of instability is exhibited. What does it mean to be a chaotic dynamical system, and how do you characterize that? What is the role of the number theory? It turns out there's a lot of hidden number theory, both, of course, in these. I was trying to visualize that number theory, but in the planetary motion, that for example, in the structure of the rings around Saturn, why are there gaps? In the asteroid belt, why are there certain places where the asteroids cannot be? The resonances are caused or modeled or explained by the underlying number theory and the number coincidences that happen, which prohibit certain behavior. So a lot of what I think about, may or may not be useful for real life and in everyday life, but it's trying to understand how does the study of the numbers and the complexity of the numbers and their interactions force geometry, force certain geometric restrictions?
Is it like the pictures in your head or on the computer somehow are inscribed in the rings of Saturn? It's amazing that there's that connection.
That's how I like to see it, yes.
So I'll do have another audience question, and this is interesting. I'm guessing the context of this question is someone is imagining you looking at picture after picture the course of your career. The question is simply, do you have a favorite fractal?
Well, do I have a favorite fractal? Well, actually, the eye is one of my real favorites, right? That eye shape that I showed you, which is why I decided to use it. So it's not the example that I happen to be studying right now. I said I generated it 10 years ago, but it really is one of my favorites exactly because of where I love the Mandelbrot set too. I spent a lot of time thinking about the Mandelbrot set, and this one has the Mandelbrot set in it. And it also is the eye. And why is it an eye? And one of the other pictures I showed at the beginning of the talk was one of the last ones. I was trying to emphasize how the pictures are surprisingly beautiful, and there was like some purples and blues overlapping, and that was actually a zoom of the eye. And so right now, I'll just say the eye.
Okay, so there are a couple questions here that I think are getting at an interesting thing that people are saying. I'm looking at the things you studied, and you would, for example, in your initial sequences, you'd start with 0. Why 0? Or similarly, in the equation or the formula that led to the I, you had a certain polynomial in the denominator. Why that polynomial? What determines sort of the parameters of the things that you study?
Yeah. So one quick answer is none of that matters, in the sense that I'm looking at any nonlinear recursion. What does matter is that I was keeping them simple. They only, in this particular case, in these examples, they only involved one step. The next step was always determined just by the previous. In the Fibonacci, it involved 2 steps, and I decided to simplify and only look at 1 step. So that keeps it as what we call a one-dimensional system. So that was relevant at least for the particular techniques that I was thinking about in the back of my mind, which I didn't talk about, but there is, of course, a lot of math happening in the background that I didn't talk about, and a lot of it did rely on it being a one-dimensional system. But also that they're either algebraic, say polynomial functions or rational functions, but they could be what we call analytic functions of that one variable as well. So there's a slightly larger class. 0 was special for the Mandelbrot set because it's the unique starting point, which is a critical point. We were looking at these polynomial recursions, and it turns out that the derivative of that polynomial vanishes at exactly 1 point, and that happens to be 0. So it's actually very special, but from an arithmetic point of view, from a complexity point of view, from the conclusion point of view of what I was talking about, it shouldn't be special. But we can prove more if you start at 0. So Hawley-Krieger's theorem that I was mentioning did use the fact that we were starting at 0 because it's this special, it's what we call the critical point for this recursion. But we expect that the conclusion of her theorem should hold no matter what the starting point was.
This actually gets at another question here, which is someone is wondering about how much you think you can generalize all of this. Like, how far do you think you can push this program? You know, is it like, could you go to higher and higher polynomials, all sorts of other points? Do you think there's some point where it's just going to like get too hard for people, or how far can you go?
Okay, so actually, what I'm presenting really and truly is like, these very special cases of a much bigger question. So I mentioned that some of the technique here were one-dimensional, but that's not even necessary. I'm really thinking about arbitrary dimensions. What is sort of the right level of generality for all these questions is an algebraic system, that there are polynomials and rational functions involved in these recursions, that you can write them down just with powers and sums and finitely many steps and finitely many inputs, so it could be higher dimensional, but it's fundamentally algebraic, and that is crucial. And so the right generality is that you might have a finite step recursion, meaning you can go back finitely many steps, and that each of the formula is some algebraic formula involving the terms. So that's the type of generality. But I'm really interested in the geometry of all that. So it's just sort of course, you can't draw it the same way if it's higher dimensional, but.
Okay, so there's a whole world out there, and like a ladder going up. And in fact, this relates to another question which came in about, you mentioned that the techniques have been changing, that the way that you work now, 21st century mathematicians, is well beyond what Carmichael was doing. Like, that your techniques are way beyond. And much more generally, like, technology is moving, things are changing, we see AI coming in now. Can you comment a little bit on sort of how these changes have worked historically? Do you feel like they're technology driven? Do you feel like they're more intellectually driven from humans? And maybe can I ask you to speculate on what you think will happen in the future a little bit? What is 22nd century mathematics like?
So, okay, well, maybe I should first say, since you mentioned AI, I definitely think that this will change the way people are doing mathematics. And I mean, right now, the way that we can use artificial intelligence maybe to help us, in the same way that we use visualizations. It's a tool, it's a supporting tool. Right now, it's not going to invent the new, like the fundamentally new ideas that we might need to solve a particular problem, but it might give you some hints, and it's very well trained on mathematics that exists already. It's very good at answering all of the homework problems that I assign to my students. It's really good at that now, unfortunately, but because it's improving and it's going to continue to improve, it's undoubtedly going to have an effect on how we're doing mathematics. That certain parts of what we do maybe can be fully formalized and done by the AI, and that could leave us to sit back and be inventive and think about, what problems should we be asking, and what where can we go with this, and how do we? So that's just the most recent piece. Of course, mathematics has developed a lot over the years. It's hard to give you a complete historical picture in 30 seconds, but one of the big changes, so really we're developing new mathematics all the time, and I mean, it's just this wild world of possibilities, and so it's just exciting to be doing math. And one of the most exciting things I just want to mention is how we do it together and with other people. And that's something I think that has evolved historically in time, that we're doing a lot more collaboration now. It's a lot more international now because it's easy to communicate with people. My colleagues who live in China or in France or in Canada or wherever, whichever country they're in, or on the other side of this country, it's a lot easier to interact and communicate. So that's one of the trends that one has seen historically in doing mathematics. Yes, technology, using computers helps, obviously. Technology affects things, but I'm not sure if it's been the driving force, although now with AI it might be.
Well, I think the excitement of this kind of global collaboration is a wonderful note to end on. And I just want to thank you for a great talk, really excellent answers to questions. And I want to say thank you to the audience. And if you want to find out about more future programming and watch videos of past events, the URL to go to is radcliffe.harvard.edu. And I want to thank you for joining us today, all of you, and have a great rest of your day. Thank you.